Hello again. So, what we just did is we used the philosophy of SOHCAHTOA, the fact that trig functions give you information about right triangles conversely, in order to do some applications. Today I want to do another type of application. I want to use this philosophy to evaluate trig functions at some carefully chosen values. So we've done some already. For instance, I know what the cosine of 0 is. The cosine of 0 is 1. The sine of 0 is 0. The tangent of 0 is 0. I know what the cosine of pi over 2 is, right? That's a right angle. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. Tangent of pi over 2 is undefined. I want to fill in the same information, but for three other angles. Pi over 6, pi over 4, and pi over 3. And in fact, what I'll do is I'll record that information in a unit circle, which I'll have off to the right. Give me a second and I'll pull that up. All right, here we are. So I'll refer to this thing as the unit circle. And this unit circle we'll solve as just a lookup table. So during the course of the rest of this video, I'll tell you what the trig functions are at 0 radians, pi over 6 radians, pi over 4 radians, pi over 3 radians, and pi over 2 radians. But in fact, two of those things we already know, as do we some other things on this unit circle. I know the sine and cosine of 0 radians. Cosine is 1, sine is 0, right? Cosine is the x-coordinate, sine is the y-coordinate. If we rotate by an angle of pi over 2, so that's a right angle, we'll end up at the point 0, 1. So cosine is 0, sine is 1. If we rotate by pi radians, we end at the point negative 1, 0. If we rotate by 3 pi over 2, we end at the point 0, negative 1. Cool. So the purpose of the rest of this video will be to use some of the philosophy of right triangles, not the philosophy of the unit circle for trigonometry, to figure out the trig functions at pi over 4, pi over 6, and pi over 3 in more or less that order. Cool. So let's go ahead and get started. So first things first, let's try to figure out trig functions at pi over 2. So let's do that. Let's do it by studying a triangle. So here's what I'm going to do. I'm going to draw a right triangle whose base is length A, whose height is length B, whose hypotenuse is length C. It's a right triangle, so this angle is pi over 2. Right, that should be a right angle. And I want to understand trig functions right now at pi over 4. So this angle is an angle of pi over 4. Because then, what will I know? Well, I'll know that the cosine of pi over 4 will be adjacent, A, divided by hypotenuse, C. So if I can figure out something about the sides of this triangle, I can figure out the cosine of pi over 4. And that's exactly what I'll do. So I'll start with this. Let's figure out this upper angle alpha. So the thing is, this is a triangle. Angles inside of a triangle have to add up to 180 degrees, or in radians, pi radians. Well, we can probably use that to find alpha, right? The three angles of this triangle are pi over 4, pi over 2, and alpha. And apparently all of those have to add up to pi. So there's an equation. Let's solve that equation. For alpha, solve for alpha. So it looks like we get alpha equal to, well, everything's going to need a common denominator of 4, so I'll get a common denominator of 4. 4 pi over 4 plus, nope. I need to subtract things to the other side. Minus, subtract this to the other side. Pi over 4 minus pi over 2, but I'll get that common denominator, so that'll be 2 pi over 4. And now subtraction is easy. I have 4 pi over 4s. I take away one of them, leaving me with 3 pi over 4s. I take away 2 more of those pi over 4s, leaving me with a single pi over 4. So this angle alpha, let's fill that in, is pi over 4. But now, take a look at this. That's a really interesting thing. How did that s get crossed out? Did I do that accidentally? Weird. So, two of these angles are the same. That angle is the same as that angle. So this angle is a so-called isosceles triangle. That crossed out S is a really weird typesetting error. I'm not sure how that happened. So if you have an isosceles triangle, then the two sides opposite the two angles that are equal, so here are two angles that are equal, the two sides opposite those angles must also be equal. So that means that the side length A is equal to the side length B. So that means that I can use the fact that this is a right triangle now to figure out what C is, right? Since this is a right triangle, I can use Pythagoras' theorem to get C squared is equal to A squared plus B squared. But A is equal to B, so I can replace that, I don't know, B with an A. So that means if I want to solve for C, I just need to take the square root of both sides, leaving me with the square root of 2a squared. There's a perfect square under that square root. I can pull it out, leaving me with a square root of 2. Now, maybe you would have wanted there to be like a plus or minus here, right? Whenever you undo a square by square rooting, generally you lose information. There a plus or minus sign will show up. But that C is the length of a right triangle, so it's a length that has to be positive. So this will just be the square root of 2a squared, which simplifies to a root 2. Oh, so now, like, I'm basically done, right? So remember, so this, on the paper version of the notes, is a new page. So I'll redraw the triangle that we have. Joop, joop, joop. Pi over 4, right angle, pi over 4, A, C. And I know what C is. C is equal to A times the square root of 2. So now we can figure out what the various trig functions are. The cosine of pi over 4, will be adjacent over hypotenuse, right? So katoa. So that will be A over C. I know what C is, though. That will be A over A root 2. The A's will cancel, leaving me with 1 over root 2. And that is a correct answer, but it's not a maximally simplified answer. In order to simplify it, I'll get that square root out of the denominator. To do that, I'll multiply and divide by the square root of 2. This is the action of so-called rationalizing the denominator. So what do you get when you do that? You wind up with the square root of 2 divided by, well, in the denominator I see the square root of 2 times the square root of 2, so that is the square root of 2 squared. But the whole point of square roots and squaring will undo that square root. That's why I multiplied and divided by the square root of 2. That'll leave me with root 2 over 2. So the cosine of pi over 4 is the square root of 2 over 2. Let's fill that in. Cosine of pi over 4 is root 2 over 2. Cool, let's keep on going. Next, we want the sine of pi over 4. So, remember that side was also called b a moment ago. So the sine of pi over 4, there's pi over 4. Sine is opposite over hypotenuse. So the sine of pi over 4 is b opposite over hypotenuse, c. But I have each of those things in terms of a. B is equal to a. C is a times the square root of 2. And we could go and do the walk again, but notice it's the same damn thing as above. I should probably be more careful about not casually squaring in class, given that this will all be recorded and available forever. Yeah. So I know what that'll be. It'll be the square root of 2 over 2. The tangent of pi over 4 will be, tangent is toa, opposite over adjacent. So that will be b over a, but I know what b is. B is equal to a over a. And I know what a is. Well, no, I don't know what a is. It doesn't matter what a is, though. A over a is 1. So tangent of pi over 4 is 1. Carrying on, let's try to do the same thing to determine the trig functions at pi over 3 and at pi over 6. So let's think about what we would need to do. In order to understand the trig functions at pi over 6, we'll want to understand what happens to a right triangle, which has an angle of length pi over 6. So let's study this triangle, which contains in it an angle of length pi over 6. So if we look at that triangle, so what will we get? So katoa. If we want to compute, say, sine, sine is opposite over hypotenuse. So if we want sine of pi over 6, there's the information we need. So let's try to figure out this triangle. And we'll start by figuring out this angle in exactly the same way as we did before. I apologize for that sudden and slightly jarring jump. Something strange happened in the recording, but let me just bring it back and tell you where we are. So I wanted to know the angle alpha, so what I'm going to do is I'm going to add up, well, I already did add up the 3 angles of that triangle. The angle pi over 6, pi over 2 plus alpha, pi over 6 plus pi over 2 plus alpha. Those are the angles inside of a triangle, so they have to add up to pi. Well, can you do that to solve for alpha? And all right, so 6 pi over 6 minus pi over 6 is 5 pi over 6 minus 3 pi over 6 leaves me with 2 pi over 6, which is equal to pi over 3. So that means this angle alpha is pi over 3. Now the red triangle is built by reflecting the tan triangle, so this angle is the same as this angle must be the same size as that angle. So that bottom angle is also pi over 3. But check this out. This blue angle is built out of an angle of pi over 6 and another angle of pi over 6. So that angle must also be pi over 3. So if you look at the big triangle, that is the triangle A, B, D, look at those angles. They're all pi over 3. In particular, they're all the same. So this is a triangle where all of the angles are equal. That must mean all of the sides are equal. That is, this triangle ABD is an equilateral. What does that mean? That means all of the side lengths are the same. Let's write down all the side lengths. So that means that this side length A, must be equal to this side length. 2C must be equal to this side length A. So that means, well, maybe I'll write it as a sentence first. The line segment from A to B, the line segment from B to D, and the line segment from D to A are all the same length, which means that A is equal to 2C is equal to A. Okay, so the first and last A, one of the two is redundant. You already know that A is equal to A. What's important is A is equal to 2C. That tells me what C is. C is equal to A over 2. That's handy. So I'm going to redraw that northern triangle again. So that top triangle has an angle right here of pi over 6. It has a hypotenuse of length A. It has a base of length B. It has a height of C equal to A over 2. but this is also a right triangle. So there's a relationship between the three sides, namely the Pythagorean formula, which says that a squared is equal to b squared plus c squared. So that means that a squared is equal to b squared plus a over 2 squared. I need to solve this for b, I guess? That would be handy anyway. So let's see, I'll rewrite that a little bit. That's a squared equals b squared plus a squared over 4. So let's see, I'll subtract a squared over 4 to the other side. That will leave me with 3a squared over 4 is equal to b squared. Now I can solve for b by just square rooting. B is equal to a square root of 3 over 2. So put that right here. B is equal to a times the square root of 3 over 2. Now I can use SOHCAHTOA. So SOHCAHTOA, sine of pi over 6 is opposite over hypotenuse. So that means that sine of pi over 6 is c over a is equal to a over 2 divided by a. Hey, that's just a half. Cosine of pi over 6 is b over a. Cosine of pi over 6 is b over a. I know what b is. B is a times the square root of 3 over 2 divided by a. Oh, so the a's will cancel and you'll just be left with root 3 over 2. Tangent of pi over 6. So TOA, SOHCAHTOA. That means that the tangent of pi over 6 will be opposite, so c, excuse the typo, divided by adjacent, b. And now we'll just write that in. Tangent of pi over 6 is c over b. That's a over 2 divided by b is a times the square root of 3 divided by 2. And lots of stuff cancels. You see both the numerator and denominator are multiplied by a. So those a's will cancel. Both the numerator and denominator are divided rather by 2. So those will cancel. That leaves us with just 1 over root 3. I see a square root in the denominator. I should rationalize by multiplying, dividing by square root of 3. That'll leave me with root 3 over 3. Very nice. So let's go ahead and take that information and write it in the unit circle up at the top of this packet. So here we are at the top of the page. The cosine of pi over 6 is root 3 over 2. Sine of pi over 6 is 1 over 2. Tangent of pi over 6 is root 3 over 3. That puts us over here. Root 3 over 3, comma, 1 over 2. Very nice. So let's go back to the bottom of the page. There's one more observation to make. Sorry, bottom of the page there meant the end of this packet. We can also figure out the same thing for pi over 3, because this angle right here is pi over 3. So we can play the same game, SOHCAHTOA. So the sine of pi over 3 should be, so sine is opposite over hypotenuse. So sine of pi over 3 will be opposite over hypotenuse. That's b over hypotenuse is a. So the sine of pi over 3 is b over a. B is equal to a root 3 over 2. Divided by a leaves us with just root 3 over 2. Similarly, we can compute the cosine of pi over 3 by looking at this picture. So cosine, ka. Cosine is adjacent. There's pi over 3. The side adjacent to pi over 3 is c. Hypotenuse is a. So cosine of pi over 3 is c over a, which we know what c is. C is a over 2. So this will be a over 2 over a. That's just a half. Finally, tangent. Tangent, toa. Tangent of pi over 3. Tangent is opposite over adjacent. So that's b over c. Will be b over c, which is equal to b is a3 over 2, c is a over 2. And you see that simplifies to just root 3. The a's cancel and the divide by 2's cancel. So let's go ahead and put that also at the top of the previous page. There we are. I've just filled in cosine of pi over 3 is 1/2. Sine of pi over 3 is root 3 over 2. Tangent of pi over 3 is root 3. Migrating over here means this is 1/2. This is root 3 over 2. Nice. So here are the important takeaways from this particular video. So I've just explained how to figure out what those values should be in the unit circle. But it's more important to know what those values are, and to also remember this philosophy that if you have a right triangle, you can use that right triangle to tell you things about the angles you see in the triangle. You can use it to write down what the trig functions evaluated at those angles are. Excellent. So that completes this lecture. I hope that you enjoyed it. I'll talk to you later. Maybe one more thing. So you'll notice that there are like 3 quadrants that we haven't touched in this unit circle. We'll come back to that in the next lecture. Great. Now I'll stop.